this is part of this is a project about particle methods for integral equations, is part of my PhD, and is joint work with my supervisors, Arno and Adam, who some of you might know. I've seen some familiar names in the audience. It won't be extremely long, but hopefully there will be enough time for questions. I try to time it in the right way. So I will try to, well, I will start by motivating this project and basically explain why we started looking at this problem, then give a bit of background on Fredholm Integral Equations mostly, and just 2 slides about SMC, because I know that the audience is quite familiar with SMC. So I will just briefly set the notation, then introduce the algorithm that we propose, which we call SMC EMS, a couple of results, both experimental and theoretical, and briefly conclude. So this is the object we are addressing in this project. This is an integral equation. In particular, is a Fredholm integral equation of the first kind. And the aim is to recover the function f given some knowledge of g and h, which usually means we have an analytic form for g, or we can approximate g with a function. And from h, we have samples or maybe some type of discretization of h. And I like to think about these integral equations as the extension of linear systems to infinite dimension, because if you look at it for a while, and you imagine that h is a vector, f is a vector as well, and in here, instead of having the integral with respect to g, we have a finite sum. This is pretty much a linear system. And so being an extension of linear systems, they model a lot of things, including those modeled by linear systems. In general, they describe the process of finding f, describes the reconstruction of a signal from some distorted version of it. And an example that I will use quite a lot during this talk is the convolution. If you think about this integral equation in a one-dimensional setting where G is a convolution kernel, so it has this form, then normally what we do in first-year probability is teaching undergraduate students that you can recover the density of a sum by computing the convolution integral. So if we say that we want the density of x plus epsilon, and we call that random variable y, then this is how we get the density. What we are trying to do here is the opposite. So we already know the density of the sum. We're trying to recover the density of one of the components. But this is just a particular case of a much more general problem, which finds applications in mostly applied maths and engineering, but there are also quite a few examples in statistics. And because it's so common, it's also very well studied from a theoretical point of view. So it's the prototypical example of an ill-posed inverse problem, where by ill-posed, I mean that we're trying to recover f. So, you know, is on this side of the equality, on the right-hand side of the equality. The direct problem would be to find h given g and f, but we're trying to do the opposite pretty much. And it's ill-posed because very often we don't have a unique solution. And even if the solution is unique, it's very unstable. So small changes in h do not necessarily mean small changes in the solution that we recover. That's pretty much why it's really hard to find good solution methodologies. And most of the time, these methodologies rely on regularization, which means instead of finding, instead of trying to invert this particular integral over here, we just set a distance between the right-hand side and the left-hand side and try to minimize that. So where do particle methods come into place? In the standard techniques which are available in the literature, they mostly come from the applied maths literature. And so a natural way to solve this problem is to assume some particular form for f. The easiest one is just to take the domain of f, perform a sort of brute force discretization and approximate f with a constant value on each of these discretization elements. A slightly more refined option is to assume that f can be written as a linear combination of basis functions. In both cases, we need some functional knowledge of h, and by that I mean that samples are not enough. We need some discretization, or even a kernel density estimator will do if we only have samples. And this is not too bad, but as you can imagine, all methods relying on deterministic discretization get very impractical as dimension increases. And even though these type of equations do not tend to be super high dimensional, so the most common applications are in 1 to 3D, with some exceptions to 10 dimension. But already in 3 dimensions, performing a discretization in like the simple version of a discretization scheme, I mean, the cost grows exponentially with the dimension. So it's already quite hard even to code. There are other options which do not depend that much on dimension and can perform really well, but they require a specific form of G. So for instance, the convolution kernel that I had in the previous slide. So by putting some constraints on G, we can build specific algorithms which work quite well. So if these are the standard techniques, what we try to achieve using particle methods is a bit more flexibility. So instead of assuming that f is a linear combination of basis functions or is piecewise constant, we just take f to be a probability distribution. And so the same assumption for h. And G is also, we see G in a probabilistic setting as well. This might seem even more restrictive, but actually a lot of the applications of these integral equations are in image processing. And if you think about an image, very often this image can be written as the discretization over pixels of a continuous density, because images, the value of pixels is a positive number. So we already have a positive function. We just need to make sure that it integrates to 1. And that's the case for a lot of the other applications. So in most cases, we are actually in the situation in which all the quantities involved, F, H, and G, are positive. And what is left is just to basically make sure that they integrate to 1 to use this SMC EMS algorithm. And because this is a particle method, it's quite natural to deal with the case in which we have samples from H rather than some functional approximation of H. There is still a discretization involved because we use samples, but on the other hand, is not set a priori. So it is adaptive in the way that the samples will move around the space and concentrate where F has more mass. And well, all this kind of started because of the dimensionality problems. So these methods have the potential to tackle higher dimensional problems, mostly because they rely on SMC techniques. And we know that those up to dimension 10, they work really well. So I hope I convinced you that this is an interesting problem. So I'm not going to move to some more background, not too much. I don't want to bore you to death with the theory of integral equations. So I will just briefly mention what is usually done in the literature. The first approach, which I think a lot of you might be familiar with, is what we do for linear systems as well, in a way, because we try to minimize this distance, the L2 norm between the left-hand side and the right-hand side of the equation. And then we add a regularization term, which in this case is given by the square norm of F. This corresponds to a model with Gaussian noise. So imagine that we have the integral equation plus some Gaussian noise on the side. Under this assumption of Gaussian noise, this has a very nice link with Bayesian inference, because you can see that this looks a bit like a likelihood, and the additional norm over here looks a bit like a Gaussian prior. So we can do something in that direction. And there are also iterative methods to solve this minimization problem. The most famous one I know of is called the Landweber iteration, which works very well in one dimension, but as I mentioned earlier, gets quite hard when you are in dimension 2 and above. The other option, and the one that I will focus on in this talk, is maximum likelihood. So instead of minimizing the L2 norm, we minimize the Kullback-Leibler divergence between the two sides of the equation. And then we can add a penalization term over here. Very much in the same way in which we had a penalization term in the Tikhonov regularization. This particular choice corresponds to Poisson noise, and that's the type of noise that is very common in the image processing field, because images can be seen as emissions of photons. So the intensity of the pixel is basically a Poisson count. And so it's quite straightforward that Poisson noise is somehow more likely than Gaussian noise, or at least in the particular settings that in which these integral equations are used. And of course, to use the Kullback-Leibler divergence, we need all the quantities involved to be probability distributions. So that fits nicely in our setup. And because of the link between KL divergence and maximum likelihood, we know that we have a big number of expectation maximization algorithms, which have been studied in the past, and we can look at those and check if they solve the integral equation problem as well and how they perform. So what I'm going to do next is give a brief overview of these expectation maximization algorithms. The very first one, which is also the simplest one, was introduced in the physics literature in the 80s, and is really a simple iterative scheme. We start from F1, which is a guess from our solution. It doesn't need to be a very good guess, because this guess is going to be refined at each iteration by taking the current guess and multiplying it by this integral over here. And this is indeed an infinite dimensional EM algorithm, in the sense that we have an expectation step given by this integral over here, sorry, a maximization step given by the integral, and the expectation step given by taking the product with respect to that integral. And because it's an EM algorithm, we have a number of results, including that it minimizes the Kullback-Leibler divergence. I think in 2017, it was proved that in the infinite dimensional case is actually converging. If we discretize this iteration scheme by assuming a very simple discretization in which the function f is piecewise constant, we fall into the EM for Poisson data. So this is also coherent with the noise model that we chose. This particular EM for Poisson data is known as the Richardson-Lucy algorithm in the image processing literature, where it's extremely popular. I would say that it's probably one of the go-to algorithms in that field. And as I mentioned earlier, all the nice properties of EM still apply, but also all the not nice properties of EM. For instance, we know that this iteration can have more than one fixed point, because we know that the EM can converge to local maxima of the likelihood or minima of the KL divergence. But the most relevant issue for this particular context is that the maximum likelihood estimator is not consistent. And this reflects in our approximations, because our Fn will be very spiky. But on the other hand, what we're trying to recover is a rather smooth function. So spiky estimates are really not what people want in the Fredholm integral equations literature. So starting from this method proposed in the 80s, there were a lot of efforts to add penalization terms or modify this Kullback-Leibler divergence so that we can ensure smoothness of the resulting estimator. Among all the options, and there are really a lot, we focused on the expectation maximization smoothing, which is a very simple variant of the EM. So the only difference is that once we have the iterate at time n, which is given in black over here, we add one step to the expectation maximization. And this step is a smoothing step and is basically given by convolving our current approximation with a smoothing kernel, which is given in red. And by doing that, and by properly choosing the smoothing kernel, this iterative scheme gives a trade-off between closeness to data in the sense of the Kullback divergence, because we know that the black part will still try to minimize the KL divergence, but the red part will impose some smoothness and hopefully give solutions which are close to the minimizer of the KL divergence, but also smooth. And so we do know a couple of results about this EMS algorithm. A lot of them are not known yet. For instance, it has been shown that its convergence is faster than the EM, but there is no proof that it is converging, even though empirically it's always converging. So I'm quite sure that convergence occurs. I just didn't know how to prove it. We managed to show that there is a fixed point of this iterative scheme in the space of probability measures if we focus on compact sets. And this basically was reassuring for us because it means that what we're trying to approximate actually exists. But there are still a lot of points which we're not really sure about. So for instance, we couldn't show that this fixed point is unique, even though in experiments it looks like it should be, which would be a great improvement over the EM. And also, because of the addition of the smoothing kernel, we cannot really find a functional that this iterative scheme is minimizing. So we know it should be something close to the KL divergence, but is not quite that. On the other hand, it works very well. And so we will look at, we focused on this EMS iteration and connect this with SMC. In contrast, what we did is in this project is also comparing with what people usually do when implementing the EMS algorithm, which is again just assuming that f is piecewise constant and approximate the integrals with sums and solve this particular iteration, which of course in one dimension is extremely fast, but as we will see is not as good as the SMC version. But in higher dimension, this becomes very, very expensive. So before jumping into the SMC EMS, I just have 2 slides about SMC. So broadly, I would describe sequential Monte Carlo methods as a class of methods that sequentially approximate a sequence of target probability densities. But most importantly, what I will really need for the rest of this talk is the dynamic that the sequence of distribution follow. So to update from time n to time n+1, we will perform a weighting step and a mutation step. So we weight what we already have and we propose a new state. If you looked at the SMC literature, or the filtering literature for a long time, you might notice that this is not the standard way in which this is presented. Usually the M comes before the G. So this would be the measure flow for the predictive distribution rather than the updated one, if that is familiar to you. But because the EMS fits better into this framework, that's the framework we worked with. And so once we identify these recursion over n and we find our G and our M, all is left to do is to approximate the evolution of this sequence of densities through a set of weighted particles. And so here I have a cartoon explaining what that means. So let's say that at time n, we have these samples over here, and what we are trying to move to, so the n+1 looks a bit like the black line. So we reweight first, and as you can see, the samples which are outside the areas of large mass are still there, but they have very, very small weights, and it's basically impossible to see them, while the ones in the middle have way larger weights. And then we resample to get rid of the particles in these areas where there is a small mass, because they didn't give us a lot of information. And after resampling, we move the samples that we have left around to explore the space a bit better. And basically that's about it. We repeat this process until we reach some criterion or until our computational budget runs out. So with these two bits of background, EMS and SMC, we can introduce SMC EMS, which is nothing more than an SMC approximation of the EMS recursion. So as I mentioned earlier, the way this starts is by seeing the EMS recursion through the lenses of SMC. So in here, I reported again the EMS recursion, where instead of using x, y, and x prime, I just added time subscripts to it. So now we have an h for time n, the f at time n. Our smoothing kernel moves from time n to time n plus 1. But if you forget about the ends, is really the same iteration that we had before. The first step, which mostly comes in because we need to make our life a bit easier and get rid of some integrals, is to, instead of consider f itself, consider an augmented density, which is given by the product of fn and h. And this presence of h over here is not really a problem, because in our assumptions, h is known somehow. Even if we only have samples from it, that would be enough. So if we define eta in this way, we can now write an equivalent iterative scheme for this eta, which looks a bit like this. And I mean, the biggest difference is that instead of having this integral over here, now the integral moves to the left, and fn becomes eta n. That's about it. And now this h over here is incorporated in the eta. And so instead of having h times n, we have h times n plus 1, which comes from the contribution of eta n plus 1. But the details are not super important. The important bit is that if we look at this eta and at this particular iterative scheme, and we think about going back in time, so getting rid of these integrals and recursively move from eta n to eta n minus 1 up to eta 1, we get to something which looks like this. So to move from time n, where, as you can see, now this eta n is defined on a much larger space in which we consider all the particles from time 1 to n. But to move from eta n to eta n plus 1, we have a weighting step given by this integral and a mutation step given by this product. So we get a new y from h and a new x by using the smoothing kernel. And that's about it. There is a more detailed proof in the preprint that I mentioned over here. Actually, not a preprint anymore, but I got used to say that. And so basically, we identified the connection with SMC, and what we are left with is just implement the code with this weight and this kernel over here. So looking at these two objects a bit more in detail. The Markov kernels are defined using the smoothing kernel, which is user chosen usually. So we can choose it to be, for instance, a Gaussian smoothing, which makes it very easy to sample from. And then we need samples from H, which is, as part of our assumption, we assume we have. The other bit that we need is a resampling mechanism, and we didn't focus too much on that. I think that most of the common resampling mechanism would apply. So you just pick your favorite one, multinomial or systematic, it doesn't really matter. Because the real difference between standard SMC in this particular algorithm is the definition of the weights. So this is what we need to compute to reweight our particles. And well, we assume that G is known, so the numerator is really not a big deal, but the denominator is slightly problematic because it involves this eta n, which is the object that we're trying to approximate. So that means that computing the weights analytically is out of the picture, and we need to approximate them. Luckily, we can approximate them, because if we couldn't, then we would be a bit stuck and couldn't do much more. So what we can do is to approximate this denominator over here with the particle approximation, which basically involves approximating eta n with the samples given by our particle system and approximate the integral with the average. And so we have these approximated weights over here, which are random, but they're also biased because of the particular form that they have. So all these means that the standard results for SMC, so the strong law of large numbers, the central limit theorems, do not apply. And so as part of this project, we also looked into extending some of those results to this particular case. But I will talk about that in a second. You might wonder how, so I talked a lot about we want smooth estimates, so the EM is not suitable, but then given the SMC algorithm that I described, it looks like we end up with a set of particles, which is not really smooth per se. So to obtain a smooth approximation of this Fn plus 1, we combine our particle system with kernel density estimation. So what happens here is that given the weighted particle population, which is basically what we obtain from the iteration above without the smoothing kernel. So let's say we stop before applying this k at time n plus 1. We use the weighted particles to get a kernel density estimator with bandwidth that goes to 0 with the number of particles. And then afterwards, we apply the smoothing kernel. The particular order of these two operations has two reasons. The first one is that we really don't want, sorry, we really don't want the bandwidth to go to 0, because that would cause our estimators to fall back into the EM, and we know that that's unstable. So by combining kernel density estimation with K, we basically make sure that even for large sample size, there is a bit of smoothing given by K itself. And the smoothing given by K does not change with the number of particles. On the other hand, we could swap these two steps and do 3 before 2. But this version with 2 and 3 in this order is just a raw Blackwell-Izide version of the other one. And so we know that that gives smaller variance, and that's pretty much why we choose to do these steps in this order. So after a lot of showing you recursion, let me show you how it actually performs. And as I mentioned earlier, I will look a lot at this density deconvolution problem, mostly because it's quite simple. It's quite simple. The particular one that I'm focusing in here is one-dimensional, which means that EMS is cheap, and we want to check if SMC EMS is cheap or better in terms of performances. Even if this is a very simple example, it has been very well studied in a lot of fields, including epidemiology, and has been used quite a lot to infer COVID-related quantities. And if we assume that G is Gaussian, sorry about that. The estimators that we also have are the convolution kernel density estimators, which are optimal, at least asymptotically. So what we did is to take a particular example and compare our options here. So in this picture, I'm showing results for 4 estimators, the SMC one, the cheap EMS, and 2 versions of the convolution kernel density estimators, and comparing their runtime in seconds and their accuracy measured through the integrated squared error. So what we can immediately see is that EMS is very cheap, but also pretty inaccurate compared to the other options. This purple line is a convolution kernel density estimator with cross-validated bandwidth, which is somehow known to perform quite poorly in some cases, and this reflects really in this picture as well. The yellow line is the cheap and efficient version of DKDE, but the blue line, which I was really glad to see when I plotted this picture, is the SMC EMS. So for given cost, it actually gives the best accuracy. And I mean, it's quite costly compared to EMS, simple EMS, but we gain quite a lot in terms of accuracy. And in particular, as we increase the number of particles, which is given by these 5 symbols over there, we gain a lot, while if we increase the number of beams for EMS, the gain is smaller. So that was quite nice. And the second check that we did on this example is how this reflects on smoothness, because I mean, we started with the EMS because we really wanted something smooth. So let's look at that as well. So what we have over here is a distribution of the mean squared error at 100 selected points in the support of F. We take this measure to measure the smoothness of F, because we would imagine that good approximations are smooth if they have the same smoothness of the solution, which is a bit arbitrary, but I mean, defining smoothness is kind of hard in this concept, in this project. So we went for this option, which looked sensible. And well, what can we see here? EM is the worst, which is not really surprising because we know that the maximum likelihood estimator is not consistent. So we would expect this reconstruction to be basically piecewise linear and with spikes instead of smooth modes. EMS, of course, is built to improve smoothness, so it does better than EM, but it still does worse than the convolution kernel density estimator and SMC. So that was also nice to see. There are a few cases in which SMC is not very smooth, but most of the time is way better than the other options. So the next step was to look at something more challenging than the convolution. Because one of the strengths of this approach, or at least we believe that is a strength, is that it doesn't require any particular form for G. So G doesn't need to be at the convolution kernel, can be anything. In this case in particular, is very much not at the convolution kernel. So this is the kernel that we use for this experiment with emission tomography. And it basically describes how this data, which is periodic, so the x-axis in this B picture is 0 to 2 pi, while the y-axis is measuring the depth, starting from 0 in the middle. And this kernel is describing the alignment between this data and the reference image on the left-hand side. And this is pretty much what emission tomography scanners provide as data. These ones are, let's say, a toy set of data, because the reference image that we have is called a phantom, and is like an image mimicking the structure of the brain, or the structure of brain images coming from emission tomography, and is usually used as like a benchmark for algorithms trying to solve these Fredholm integral equations. And so, as you can see, I mean, there is really not much connection between the noisy data and the reference image. We really need this complicated kernel to see how they can be meshed up. And so, even if this kernel is not a deconvolution one, we can still get pretty good reconstructions, which are shown in the last picture on the right-hand side. The computational cost is not huge. I think these run on my laptop for about 12 minutes to reproduce this reconstruction over here. And then, of course, you can set the number of particles to give more accurate reconstructions, but the running time will increase. But that was reassuring to see that is not specialized to any G, but it can tackle a very large class of G. The last example that I have is, again, a bit of a toy example, is a deconvolution problem in D dimensions. The reason why we looked at this is because one of the strengths of particle methods is that they should scale well with dimension. So we checked that. In this case, we cannot use convolution kernel density estimator. And EMS gets very expensive. So check that we did was a direct comparison of EMS, discretized, and SMC EMS. And these I just have a couple of pictures which show dimension and the ratio between the mean squared error for the mean of the two algorithms. So what we wanted to see is that these box plots should be above 1, because that means that SMC EMS is doing better. And they have roughly the same computational cost. So we set the number of particles to 10,000 and obtain roughly a matching number of bins for the EMS, which means that in dimension 2, we have a fair number of bins, 100 per dimension, but in dimension 5, this goes down by quite a lot. And we can look at more plots like this one. I have another one. This is the probability of a particular region, and we see that in this setting, small dimension, there is not a big difference, but as dimension increases, the difference gets larger and larger, which from my point of view means that if you have a 5-dimensional problem, you're probably better off using SMC EMS rather than EMS itself, which was pretty much what I was hoping to obtain. As I mentioned earlier, we also have a few theoretical results, but I'm aware that I'm running out of time. So I will just briefly comment on them. We have a couple of assumptions. Mostly they are fairly reasonable. The first two might look a bit weird if you are very familiar with the results in SMC, because usually we really don't want X and Y to be compact, but they fit with the integral equation literature. If you think about images, most of the time, I mean all the time, images are defined on squares or rectangles, which are compact domains. And the last one is really that when we choose our smoothing kernel, it should be a nice kernel, so continuous and bounded. If all this is satisfied, the particle system is well behaved. And by that, I mean that we have convergence of order n 1 over square root of n, which is the number over here, for LP errors, which is one of the standard results people look at in the SMC literature. And then from this, we can recover a strong law of large numbers and convergence in the weak topology, which is particularly interesting because it means that even without taking integrals, our particle approximations are converging to the EMS recursion. And well, the way this works is that you just have to take into account the fact that you have approximated weights and control the error caused by that. We looked a bit also at the properties of the estimator itself. So we need the bandwidth to go to 0, as for every good kernel density estimator. But we also know that we have the additional smoothing given by K. So we don't need the rate condition on the bandwidth, which is quite common in the kernel density estimation literature. And we can show a couple of results, which I'm not going to go into the details, but pretty much they mean that in all sensible situations, our estimator should perform quite well. So it's close in many different ways to the truth. Okay, that's all for convergence results. To conclude, well, to summarize what I described over here, we proposed a novel method to solve Fredholm integral equations, which is adaptive in the sense that the particles move around to areas in the space in which there is mass and information, and is based on this EMS recursion, which has been around for a while. In the experiments that we have, it performs better than the deterministic EMS, and also then performs better than some specialized algorithms. And we managed to show some theoretical results as well, which basically suggests that the scheme is a well-behaved SMC scheme. And yeah, that's everything. And thank you for listening.
Thank you so much, Francesca. What a fantastic talk. I've got a few questions, but I might just open up to the floor to see if anyone wants to jump in and ask something first. Or online, feel free to unmute yourself. And Leah, yeah.
Thank you. That was a really great talk. So I have a question about the kernels. So firstly, I'm kind of wondering, is it the kernel that's used in the smoothing after the fact, is that the same kernel that's used in the SMC? And then also, if you could give a bit more guidance, does Gaussian kernel work well in all of the examples you used? So
we presented this in a very general setting, but in practice, in the experiments that we have, we always picked this kernel density estimator, which we only perform at the very last step, basically when we want to get the picture, to be a Gaussian kernel. And the smoothing one, which is what we use to update our particles, is a Gaussian kernel as well. So throughout the running of the particle system, we only propose using pretty much a random walk. And then at the very last time step, we use this Gaussianity to make our life a bit easier and just add variances and compute something which is way easier than using, maybe more sophisticated kernels. And about the choice of how much you smooth, that's a really good question to which I'm afraid I don't have an answer. Like, in my head, there are two possible ways. The first one is that in some cases, you have some information on the smoothness that you want. For instance, I don't know, in the convolution problems, usually, you know that the solution is slightly less smooth than the data you observe. So you could estimate the variance from the data and maybe say, I'm going to reduce this by epsilon. The other option would be just use cross-validation. But because we don't really have a functional, it's hard to tell which functional you should use when you do cross-validation. For instance, maybe a KL divergence will do, which is what we do in the experiments.
Right, that sounds sensible. Thank you. Really impressive work.
Thank you.
Sorry, he's got a question from Lawrence who's coming up to ask.
Hello, Francesca. Thank you for a great talk. I have a question about normalizing constants in SMC. To my knowledge, in many forms of SMC, normalizing constants are trivial computation. Is that the same in this case? And would you be able to use them for model selection for deconvolution?
So yes, they are available, but we know because of the particular form that we have that the normalizing constant is 1. So if you look back at the iteration that I have, which is really messy, I can see that. It was kind of hard to fit in one slide as well. But we have a more detailed proof in the paper. Just by integrating out, it turns out that everything goes away and the normalizing constant is 1. So I actually never thought about using, like doing some sort of model selection to choose this smoothing kernel. But I'm not sure if we could use the normalizing constant because of that reason.
Thank you for your answer.
I had a question about the biasness of the weights because you use the particle approximation for the denominator. Technically, how did you work with that and still get your convergence results? Because that's a problem for the convergence results, right?
Yes.
Yeah.
I think that we managed to obtain the LP inequality and the bias, even with bias weights, because we can exploit the fact that the space is compact, which normally you wouldn't want in an SMC algorithm, but we need those assumptions for the theoretical results on the integral equations anyways. And the fact that because it's compact, G is bounded below. And G is very much involved in the weights, but because it's bounded below, I can bound the denominator below and above as well. That's pretty much how we did that. But we also tried to obtain a central limit theorem, which we didn't manage so far. And to be honest, I think we gave up on that because it proved to be too hard, because these random weights give you a product of random measures which are dependent. And so, yeah, if we can exploit the boundedness below, the LP inequality follows quite easily by using the inductive approach. Is not super hard. But more involved results, I really wouldn't know how to deal with them.
That's really interesting that the compactness is one of the main things that helps you get there. I'll have to look at the paper a bit more closely.
The other option, I think, for this particular problem is that maybe you can get away with, instead of compactness and bounded below, some tail condition on G. So if G doesn't decay too fast, yes, if it doesn't decay too fast, you might be able to get the same results. Well, I didn't check.
Okay. Right. Were there any other questions? I had one other thing. I think you mentioned that the smooth version of the iterative updating had it did or didn't have a objective function that you could think as if you're optimizing that.
In the continuous case, so the iteration I presented, I haven't managed to show that there is one.
Okay.
If you discretize everything, which was how the EMS was introduced, is in this discrete version. So if everything is discrete, you can show a lot more. So in that case, you can build a functional, which is like a penalized likelihood, but that involves the inverse of the smoothing matrix, which in the infinite dimensional case, if you do all the same steps, you are left with the inverse of the smoothing operator, which I know doesn't exist.
Okay.
Because that operator is not invertible. So I got there and then I was stuck and I didn't really know.
I think it's a good place to get stuck, to know that it's not invertible.
Yeah, despite my PhD thesis being on particle methods, I did look a lot of functional analysis for this project.
It's good to have lots of tools to use.
I mean, yeah, it has been great and it turned out to work quite all right. So I'm happy with that.
Yeah, your results are fantastic. We're really happy to have you present them here today. And hopefully next time you'll be presenting in person, or maybe a few of us will be overseas and you can present in person overseas. But it's been...
I would love that. We are slowly starting to have meetings in person again. So that's refreshing.
Yeah. Fingers crossed, a safe but continual progression towards something closer to normality. Anyway, if everyone would join me in a virtual and physical round of applause. Thank you so much, Francesca. So great having you.
Thank you.